In this chapter, we will be exploring topics in set theory. In this lesson, we will be introducing the concepts of sets and elements and other ideas related to set theory.
So in this chapter, we're going to look at a different branch of mathematics than anything you would have looked at previous to this point here. But don't let that throw you off here. In many ways, when we talk about set theory, we're talking about a form of mathematics that's actually very instinctive. What we do in set theory here, what it says right here is it's a study of the groups of unique objects and the relationships between objects within the group here. Okay, now when you're born, you are instinctively doing a set theory. You're breaking things into groups here. I like this, I don't like this. This makes me happy, this makes me sad. So you're kind of classifying the universe. Okay. Anyway, so that's essentially what we're going to do here. Now to start off with, we're going to just look at some definitions and some notation here. Specifically, let's talk about a set. A set is a collection of distinct objects. Now, we want to be clear here. When we talk about set here, there is an unambiguous rule for membership. That's when we talk about a set. Okay, there is an unambiguous rule for membership here. So you should never. You'll know that you've got a set. You're looking at a proper set here. If no matter what you look at, you're never in a situation where you're like, well, does this belong to the set or doesn't it? If you're looking at it going, well, I can't tell, then your definition for that set is not very good. Okay, it should be an unambiguous rule for membership. Typically, we're going to use capital letters to identify the name of a set. Okay, like set A. When we do that set A, it would be capital A, or like they have the example down here. Set V is a set of vowels. Okay, and then we use our braces here. Okay, to encompass a set. Okay, now just little things about this. When you put stuff in a set here, order isn't important. Okay, order isn't important, particularly when you're putting stuff in braces here. Let's just zoom in on that a little bit so you clear here. When you've got these kind of brackets here, if you will, order is not important. Now, if you did something like this, if you put parentheses and you had A, B, C, and so on, as soon as you put that, order is important. Okay. In fact, we would call this an ordered n-tuplet. Okay, because in this case you got four terms here, so this is an ordered tuplet, okay? Because when you put the parentheses there, you're implying that the order that the numbers come in, or the letters, or whatever it is, the order is significant. But when you're dealing with sets, order isn't important, okay? I'll zoom out a little bit here. Another word we want to talk about here is element. Now, any item that is part of a set, any object that's within a set, is typically going to be called an element, okay? And then we denote membership. Okay, so membership in a set, okay, is usually denoted by the symbol, this guy right there. Okay, let's zoom in on that. That symbol right there, element of this. Now, you've probably seen that symbol before. Odds are pretty good if you've gotten to this point right here. You have seen, for example, where we might say X, and some people just say XER, and you're not entirely sure what the heck that means, but you've been using it, for example, to talk about domain or range or whatever. And this simply means that the element, the variable that you're choosing, is in the real numbers, the set of real numbers. So when you were using that before, you were using a bit of set theory there. And then if we put the little line through it, we're indicating that whatever element you're looking at here is not a member of that particular set. Okay? So yeah, so that little epsilon there is really the name of it. Epsilon indicates membership in a set here. Now, you have looked at different sets before. Okay, this would have gone back a couple years already. So let's just take a quick look here. The set of whole numbers, remember that was 0, 1, 2, 3, and so on, ad infinitum. You know what? I have a heck of a time drawing those out now. There we go, nicely. Integers. your integers were the set of, well, those go on forever to the left there, to the negative there, so -3, -2, -1, 0, 1, 2, 3, and then they go on forever like that. So those are your integers. Natural numbers, remember these are your counting numbers, if you will, so they start at 1, 2, 3, and they go up by ones like that. The prime numbers. Now, probably should be a symbol here. It should be something equal to that. But anyway, the prime numbers. What's the first prime number? Now, if you said 1, no. In fact, when you define prime numbers, 1 is actually specifically left out. Okay? Prime numbers are numbers whose only proper factors here are going to be 1 in itself. And then there's a little bit more to that definition, and where they specifically exclude the number 1. The first prime number is actually 2, and then 3, and then 5, and then 7, and then 11, and so on. Okay, and there you go. Those are our prime numbers. But here are just some examples of some sets that you probably have seen before, played with before. Away you go. Now, there are 3 ways that we can write a set. Okay, the first one here, we're going to list the elements in the set. That's, you know, when the sets are small, this is probably the best way to do it. You just identify the name of the set. Set A is equal to this little group of objects, 1, 2, 3. You just list them off. Another way to do it, though, would be to give a description of the set. Okay, like you describe it using words. So, A is the set of natural numbers less than 4. Okay, well, here's our 1, 2, 3 again, right? Natural numbers start at 1, less than 4, 1, 2, 3. The third way of doing it is to use set builder notation. And we're going to try to use this as often as we can, because it's just a nice, efficient way of doing things. And it looks something like this. This would be, I'll zoom in on this to identify the parts here. So here's our name. I'll go through and talk about the parts here. So here's the name of the set. Okay. The brace there indicates that we're talking about the set, obviously. Okay, the braces here are identifying a set. Now, here we go. This is going to be a set of x variables. Okay, so this is the set of x variables. Basically, we're going to call everything in here is going to be represented by x. Such that the little line that goes straight up and down here is basically just taking the place of the words such that. Now, I know that might seem goofy, but there is a flow to this. Okay, this is the A is the set of x variables such that x is less than 4. So here is the defining feature. Here is the rule, if you will. Okay? And actually there's 2 parts to the rule. So we might think of it like this. There's 2 parts to it. The first part is that the variables x here, okay, it represents numbers here. Okay, well, it's going to represent values here. It's going to represent natural numbers, where those natural numbers are less than 4. So A is the set of x values such that x is less than 4 and x is a natural number. And then you would know, oh, from there, yeah, you mean 1, 2, 3. Okay? But don't get thrown off by the notation here. This little part here tends to confuse people. This is all it means. Just this is the set of x's. Okay, so we're going to use x to represent all these numbers here, and that means such that, and then whatever comes after that, that is the unambiguous rule for defining membership in the set. That's all it is. Okay? And now, lastly, before we go through some examples here, sometimes we're interested in the number of elements in a set. Now, that's going to be particularly true when we start to transition over into discussions about probability. Because probability is really based quite a bit on set theory, okay, on understanding how sets work. So the number of elements in a set A, if you're going to write that, you would write n of A. This is not n multiplied by A. This is like a function notation here where n is the function. And n refers to the number of elements in, and then inside the parentheses here, you're going to identify the name of that set. Now, in this case up here, if we're continuing with the same definition of set A, 1, 2, 3, then the answer to n of A is going to be 3. There are 3 elements in A. Now let's take a look at some examples.
Answer the following questions given that A is a set of whole numbers less than or equal to 8, and B are the even numbers less than 10.
All right, so question 1 here. We're looking at, what do we got here? Set A is equal to the set of whole numbers less than or equal to 8. Okay, now, for the first part of this question is going to be list the elements in each set here. Okay, so whole number is less than or equal to 8. Whole number starts at 0, so 0, 1, 2, 3, 4, 5, 6, 7, and then less than or equal to, so we are going to include 8 at the end there. B, the description is even natural numbers less than 10. Even natural numbers, so it's not 1, but okay, 2, 3, 4, 5, 6, 7, 8. Now it says less than 10. My next one here would be 10, but I don't want that. I want less than 10, so there we go. Okay, so there's me listing off the elements in those sets here. So this next question says, write each set using set builder notation. Okie dokie. Now I can use whatever variable I want here. I tell you what, just for consistency's sake and to try to make this as clear as possible so you're relating these, let's say that set A, capital A, is equal to little a variables, okay, such that A is less than or equal to 8, where A is an element of, and then we would use W for the whole numbers. Now, I'm going to use a more proper notation for that. Typically, when you're talking about number systems, there's another line in the font. Okay, we use kind of a weird font for the number systems, simply so that when you see a weird W like that with another line in it, you look at that and go, oh, yeah, you mean number system, you mean whole numbers, okay? And that's all that is. Same thing with B. In this case right here, we're going to make, and I'll use little b for this, the variable, so little b such that, okay. Now, this is a little bit harder to use this set builder notation for, because of the restriction that it's got to be an even number, right? Because we gotta build these even numbers here. So what we can do here is throw in another variable here. So what we're going to do here is I'm going to say that b is equal to 2n. Okay, b is equal to 2n. Now what I got to do here in my set builder notation is I have to identify, well, what is n? Okay, where n, now I'm going to let n be a natural number here. Okay, in a little bit here I'm going to identify that n is a natural number. Now watch what happens here. 1, 2, 3, 4. 1 times 2 is 2. 2 times 2 is 4, 3 times 2 is 6, 4 times 2 is 8 here. I'm going to let n be the natural numbers less than or equal to 4, and I'll have to state here that it's going to be a natural number. And now look at what this is saying. This is the set of b values such that b is equal to 2n, okay, but n is a natural number less than 4. So there's my 2, 4, 6, 8. Now notice the benefit to saying that this part right here, b such that, because I have another variable in here, but that's not what I'm trying to use. I don't want you to get confused here. I want you to know what actual numbers here are elements of the set. The natural numbers less than 4, that's not the set. The set is the b values, and b is twice those numbers. Okay, I hope that makes sense here. This is a more complicated way to do set builder notation. Okay, but if you just read it through here, it follows. Okay, it flows quite nicely here. So this last little part here, n of a. Remember what that notation means. This is the number of objects in A. Well, the number of objects in A here looks like 9 to me. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. And we've already established that the number of objects in B is 4. In fact, we kind of needed to know that so I could do my set builder notation. Okay, there you go.
Write the following sets using set builder notation.
Okay, so right here with this question here, we're going to practice building or putting these sets in terms of set builder notation here, because it's not always a super straightforward thing to do here. Let's take a look at this one. Okay, let's call this the set, and this time I'll use the variable x, because I don't know what the name of this thing is. I don't know if there are any shortcuts, so we'll just use x, such that. Okay, look at what I've got here, 3, 6, 9. Okay, well, it would have been nicer if these were just like, 3, 4, 5 sort of thing, or whatever, but it's not. So what I'm going to do here is I'm going to state that x has got to equal 3 times n, So again, I'm going to introduce this other variable here. But remember, it's going to be the x values that are at the actual set here. I'm just going to use n to help me get that. And I'm going to let n be less than or equal to 3, and n is going to be a natural number. Okay? So the natural numbers less than 3 will be 1, 2, 3, and if you multiply them each by 3, you're going to get 3, 6, 9. Now for this next one, we're looking at a really similar sort of problem here. Okay, and again, what I'll do with this is I'll use x because I don't know what the name of this thing is, so I don't know if I can. I can't come up with a little variable that's related, make it all kind of nice and cute. But anyway, so x, such that, well, 5, 10, 15, 20, 25. So we've got multiples of 5 here, so we'll let x equal 5n. But this time we're going to let n n is going to be less than or equal to 5. But you know what? I want to include the 0 at the bottom there. So I can't let n be a natural number. I got to let n be an element of the whole numbers, because the whole numbers will go back and include the 0. Okay? And so that should be enough for me to identify 0, 5, 10, 15, 20, 25. Perfect.
Complete the following table.
Okay, so we're going to fill in this table here. We got a bunch of different things to do here. So let's take a quick look at this first one here. So the description is natural numbers between 2 and 6 inclusive. Okay, so inclusive meaning I'm going to include the 2 and the 6 here. So the natural numbers, the list of the elements here, I'll put that in set notation, will be 2, 3, 4, 5, 6. There we go. So that's going to be a set of x values such that x is going to be between 2 and 6, where x is the element of the natural numbers. Yep, like that. And then what do we got there? Looks like there are 5 elements. 1, 2, 3, 4, 5. Yeah. So n of p is going to be equal to 5. Good. Now the next one. Whole numbers less than or equal to 3. Okay, less than or equal to 3. First of all, whole numbers going back down to smaller and smaller here. But the smallest I can get is 0 because we're talking about whole numbers. And then 1, 2, and then 3. Okay, so that's the elements of the set listed out here. Now in set builder notation, okay, we'll do this a little differently here. Now I've got, it looks like everything's being labeled P, so I'll stick with that, P. It means n of P up here, blah, blah, blah. So this will be the set of, we'll use x again, why not? X values such that, now in this case here, what I can do is I can actually just state that x is less than or equal to 3, where x is an element of the whole numbers. Okay, that's really exactly what this is saying. Less than or equal to 3, whole numbers here. Less than or equal to 3, whole numbers here. That's perfect. That's all I need to do here. And I can tell by looking at this, that my list here, that the answer to this is going to be 4. Now look at this last one here. The only one that I've been given here is this one. So let's look at the set builder notation, what it says here. P is going to be the set of A values such that A is between -3 and 2, and A is an element of the integers. Okay, so this is going to be all integers between -3 and 2 and including -3 and 2. So this would be -3, -2, -1, 0, 1, odd 2, and there we go. And there's where we end there, okay? So the number of values here that we've got to answer this last question, just count it out, 1, 2, 3, 4, 5, 6. Okay, 6. And now I got to describe this in words. Okay, so this is going to be integers between -3 and 2, but I want to include the endpoints as well, so I would say inclusive. Integers between -3 and 2 inclusive, and there we go. Yeah, good. Nice little bit of practice with all the different forms of representation.
Now we'll introduce the ideas of a universal set, subsets, and the empty set.
Okay, now we're going to look at some other definitions, things that you should know when we're talking about set theory. We'll start off with the universal set. Okay, the universal set is this list of all elements in the set under consideration. Now, it's don't even think of it. You might not want to think of it as in the set or in the sets. Maybe might be a better way to describe this. In the sets under consideration. Essentially, we use the letter U to represent this universal set, and what it does is it represents everything. Everything. Or or we use a box. Okay, sometimes we're going to use just a box to represent the universal set. Essentially, everything inside the box is the universe. There is nothing outside the box. Okay, we don't consider anything outside the box. We're only interested in things inside the defined universe. Now, the universe can be anything. It could be a classroom of students. That's it. That's all we're going to talk about is just the people in this room. That's it. It could be a city, a country. It could be anything. It could be just a little set of like the fruit in your fridge. Like it doesn't really matter what it is. But as long as that's the only thing we're going to consider, these are the only elements that we're going to consider in this discussion, that becomes the universal set. Everything in that little box there is the universal set. So once we've got the universal set, now we want to start talking about subsets. Okay, so sets basically within sets. Okay, so is a subset that contains some or all, or possibly none, because that can happen, of elements from a previously defined set. Okay, so like I said, it's a set in a set. Okay, but it has to be, if you're going to do this at all, it has to be totally inside. It can't be a little bit inside and a little bit outside. That's different. Okay, so it's got to be completely within, and we'll show you some diagrams of this in just a second. We use this symbol right here, this kind of sideways U, to represent a subset, and then we'll put a slash through it if what you're looking at isn't a subset, if you actually have to make that statement and say that no, this isn't a subset, okay? And now when you say that it's not a subset here, again, we might be indicating that they're not that it's not within. So for example, let me draw something like this. Okay, we're going to start drawing sets in a second. Let me show you something that's not a subset. So here's A, here's B. Okay, well, B is not inside that set A, so B is not a subset of A. But additionally, you might draw something like this. Here's A, here's B. Now, B is partially in A, but because it's not all in A, again, you would say B is not a subset of A. In fact, the word that we give for that would be intersecting sets. Now, over here, you get a nice visual as to what's going on here. Now, bear in mind, the box here is your universe. Okay, this big circle here is going to be set B. That little circle there is A, and so A is a subset of B. It's all within B. Here, we switch it around. This is set A, this is B. B is a subset of A. Okay, A in this particular case here is not a subset of B. Okay, it's just not true. Just like over here, okay, B is not a subset of A. It just doesn't work like that. Here, we've got these nested sets. So C is a subset of B, which is then a subset of A. I mean, we could also write here that C is a subset of A, and that would work too. That follows directly from what we're looking at here. And in every one of these cases, the big box that we're looking at here, represents the universe. Okay, the only things we care about are what's inside that box right there. So, again, another way of doing this would be to list out the elements. So set A is going to be the set 1, 2, 4, and set B is 1, 2, 3, 4, 5. So now, which is true? Is A a subset of B, or is B a subset of A? Okay, well, it helps to notice which one is the smaller one. Well, A is the smaller one. Do you see all of these elements inside B? And yes, you do. 1, 2, 4. So yeah, we would say that A is a subset of B. In fact, the best we could say over here is that B is not a subset of A. Okay? Now, let's consider just another one to help us out here. There's another idea here that we want to get to in just a second before we look at some more questions. Consider the universal set D. We've got 0, looks like we're going all the way up through 9. And then the set O here, 1, 3, 5, 7, 9, is a subset of the universal set of D digits. Therefore, okay, we might write that O is a subset of D. Okay? Now, also, we would know that the number of elements in O is going to be less than Now, it could be less than or equal to, because there's argument to be said that a subset could be the same size here. But anyway, the number of elements in O is going to be less than the number of elements in D, the universal set. Okay? So, I mean, there's a couple things that you could write out there, but that's what we're getting at here. This is the universal set. That's a subset of it. Anyway, there we go. Now, a set with no elements is called the empty set. Now, and this is so important. Oh, it's so important to have this idea in place here in this lesson. The empty set is not a set with 0 in it. Okay, it's not this. This is not that set right there. No, no, no. This is a set with a number in it. That number is 0. What the empty set is, okay, it's denoted by this. It's just braces with nothing in it. It's the empty set. There's nothing in it. Okay, or it could be this symbol right here. Okay, which is just the 0 with a line through it. But you'd never do this because this is a set of empty set. And I know, that's starting to sound kind of weird here, but that's what you've written if you write this. You don't want to do that. That is a set with an empty set in it. Okay? And one little idea that it becomes necessary for you to grasp this, but it is kind of a weird one. Every set contains the empty set. No matter what set you're talking about here, the empty set is always a subset of a given set. Always. It's just the way that works. Okay? Now, a couple more little things before we start looking at some questions here. A complement. The complement in a given universe here is the opposite of what is in set A. And sometimes it's written as A with an apostrophe there, or A bar, what we would say not A. Okay? In either case here, what happens here is if you've got a set here, the complement is what's outside. It's still in the universe, it's just the opposite here. And in fact, the best way to think about this is the number of objects in A plus the number of objects in not A is the number of objects in the universe. It covers the whole universe. Okay? Yeah, that's probably the best we can say right now. And it's reiterated here, the sum of the number of elements in a set and its complement is equal to the number of elements in the entire universal set, because that's what a complement is. Together, they equal the whole thing. In fact, if you did this, if you said A plus A primed, just adding the sets together, you would get the universal set. Okay, so here's some stuff that you just need to know here. Okay, A primed is the complement. The 0 with a line in it is the empty set. Now, some things here that we haven't specifically mentioned yet. We haven't mentioned intersection and union yet. We're going to get to those in a little bit here, and those are going to kind of become, they'll become clear in just a little bit, but you're going to have to see what these are here. Intersection is kind of a combination, it's about where sets intersect, or overlap, I should say. I shouldn't use the word intersect to define intersection here. So that's going to be something like this. So here's a set, right here is their intersection. Okay? Union is when you've got a set here, let's say a set here, and then what we do is we consider all of them. Basically, it's like, in a sense, like joining them together. They're all going to be considered one big thing here. This is where the intersection is where they're both true. You're looking for elements that are in both sets. And in this one right here, I'm looking for elements that are in either set. It doesn't matter, and then they're considered part of this union of those two sets. Anyway, we will talk more about those in just a little bit here. So now we're going to move on and let's do some examples.
Complete the following table.
Okay, so here we go. We're going to complete the table. So here's our universal set. It's the letters of the alphabet. This little set here is the vowels. Okay, so now we're supposed to identify the complement. Okay, well, the complement is going to be everything that's a consonant here, so C. So A, B, C, D, E, F, G, H, not I, J, K, L, M, N, not O, P, Q, R, S, T, not U, V, W, X. Now Y, that's interesting. Well, it doesn't show up over here, so we're gonna throw it in the complement here, Y and then Z. And there you go. So all of the consonants. There. This next one here is wanting us to identify the universal set. but this time we've got this set here and its complement. Remember, putting those two together is what's going to give me the universal set. So my universal set's going to have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this is going to be the set of values here, and let's call this, I don't know, well, U for universal set. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So all the digits. Okay? Now, over here, if X is a subset of the universal set and the number of elements in X is 35, and the number of elements in the complement of X is 45, then the universal set's got to have the sum of those two. So this is going to be the sum, the number of items in X plus the number of items in the complement of X, and that will equal, well, 35 plus 45 is going to be 80. So there's 80 elements in the universe. Let's look at this next one here. The universe is the natural numbers from 1 to 100 inclusive, so we're including the endpoints here. X is going to be a subset of U, and the number of items in X is going to be 15. Okay, well then how many are in not X? Well, that's going to be the number in the universe minus the number in the original function, so that the number in the complement is going to be the difference between those two. And in this case here, we've established 100 numbers in the universal set. The set that we're interested in has got 15 in it, so the number that are in the complement of that set will be 85. And then down here, the number of elements in the universe here is going to be 110. Okay, this time we're looking for the number in this set right here. The number in the complement of this set is 100. Well, actually, that makes the math a little bit easier here, because again, this is going to be the number in the universe minus the number in the complement will equal this, and that's going to equal 10. 100 in the universe, 110 in the universe, 100 in the complement, 10 in the original.
If the universal set is the set of natural numbers, then what is the complement of the set of multiples of 3?
So here we go. So the universal set is the set of natural numbers. Okay, so it's important to remember that that starts at 1, 2, 3, and so on like that. It's the set of those values right here. Now, we're identifying a set multiples of 3. So those would be 3, 6, 9, and so on. So the complement of that is going to be everything else here. So we're looking at sets here that have purposely avoided those numbers here. Now, it can't be A, because the universal set is the natural numbers. There is no 0 in the natural numbers, so there's another digit here that's not being included, or another number that's not being included, that's not part of the universe. Can't be that one. I'm missing 1 here. 1 is not a multiple of 3. I'm missing 4. 4 is not a multiple of 3. It can't be this one. These are the multiples of 3. I mean, that's not the complement. The complement isn't itself. Well, it's got to be D. Let's just check here. 1, 2, missing 3. 4, 5, missing 6. Yeah, that's the one. That's the one I want. D.
Identify the elements in the following sets and then answer the question below.
Okay, so in this case we want to identify the sets and then just answer a couple of questions related to those. So list the elements of the sets here. Here we go. Prime numbers less than 20. Okie dokie. Okay, that's going to be 2, 3, 5, 7, not 8, not 9, not 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. There they go. Prime numbers less than 20. There's all of them. And natural numbers of 4 that are less than 20. Natural numbers that are multiples of 4. Okay, so 4, 8, 12, 16. Now, less than 20, we're not necessarily including the endpoint there, so we can't include it there. Positive factors of 20. Okay, so, well, 1 is a factor of 20, so is 2. 4 is a factor of 20. 5 is a factor of 20. 10 is a factor of 20, and so is 20. So there we go. Okay, here's a fun one. The set of x values such that x is equal to 4n. Okay, good. I got that. X is going to be 4n. Now, what are the n's? N's are going to be the natural numbers from 1 to 4. Okay, so when n is 1, x is 4. When n is 2, x is 8. When n is 3, x is going to be 12, and when n is 4, x is going to be 16. Q is the prime numbers between 24 and 28. Okay, well 25 is not prime, 26 isn't prime, 27 is not prime. There are no primes. So that's just going to be the empty set. Okay, or if you like, you want to write it with a big 0 with a big line in it. Okay, be the empty set. Now here we go. Answer true or false to the following here. Is O, okay, now O is 1, 2, 4, 5, 10, 20. Is that a subset of n? Well, n is 4, 8, 12, 16. O, no. No, and that is not true. O is not a subset of, in fact, O is bigger than n. So it can't work like that. Is the number of elements in M 8? Let's go to M. 1, 2, 3, 4, 5, 6, 7. Yeah, that's true. Number of elements in M is 8. P is not a subset of N. Okay, P. Okay, P is 4, 8, 12, 16. Well, N is 4, 8, 12, 16. Well, it turns out they are the same set here. Now, okay, it is arguable. It is arguable that it's not a subset of n. But I believe the assumption in this case is that even if they're equal to each other, we would assume that they are subsets of each other. So we would say in this case that that's false. Now, there is a little bit of an argument to be made based on the notation here that maybe this should be written differently, but I believe the assumption here is that that should in fact be false. P is a subset of n.
Given the sets A, B, C, and D, answer the following true or false questions.
Okay, so here we go. So we've got the sets A, B, C, and D here. So remember, A is Q, B is going to be PQR, C is RS, and D is PQS here. So we're going to say which ones here are true or false sort of thing. So is Q an element of A? Yes, it is. Yes, it is. It is an element of A. In fact, it's the only element of A. 2. Is A a subset of B? Now, does that mean basically, can I find the set A inside the set B? And yes, I can, because there's a Q in there. And so yes, that is true. A is a subset of B. The elements of A can be found in B. Is B a subset of A? No, that is false. Okay, it's not true because B is bigger than A. I mean, at the very least, that's why. But then the only element that they share is Q. In order to be a subset, P and R at the very least would have to be an A. So there we go, false. Q is not an element of C. Okay, well, C has R and S in it. No, Q's not there, so that's true. Okay. C is not a subset of D. Okay, let's take a look at C and D. So C is RS, D is PQS. Okay, well, these are intersecting. They intersect at S. Okay, they both have the S common, but there's no R in D. And because I can't find all of C inside D, no, this is true. C is not a subset of D. Is D a subset of D? Okay, yes. We are going to run with the assumption here that that's true here. There is some argument to be made that maybe it's not if we change some of our notation here or change some of our vocabulary here a little bit. We're not going to go into this in that kind of depth here. So what I want to do is I want you to remember that D or a set is always a subset of itself. We're going to run with that kind of an assumption here. Okay? And then finally, the empty set is a subset of C. Yes, that's true. I don't even have to look at C to know that that's true. The empty set is a subset of all sets. Okay? That's just true, period.